to make sure you guys are all set.
I think so. He's got another mic on.
He's got another mic.
Yep.
Somebody that's going to introduce might be able to use this one.
That's absolutely right.
You want handheld or are you okay with this? That's fine. Okay, you guys are all set?
Last call for refreshments.
That is key.
Last call for refreshments.
No, it's like a modern game. Anyway, Tim, thank you so much for coming. I'm Rick.
Sorry, Rick and Tim.
Rick Gate School. No, thank you so much for coming. Really appreciate it.
I'm all set. Are you? Oh, I might be muted. No, I don't think I am. I think we're good. Let's just, yeah, go for it. All right. I have the distinct pleasure of introducing our colloquium speaker today. Tim Stelzer is from University of Illinois at Urbana-Champaign. He's going to talk to us today about his path into physics education research. Tim did his bachelor's degree at St. John's University and PhD at University of Wisconsin at Madison. He is a high-energy particle physicist by training, which means I can't tell you what he did or how he contributed to that field, but I'm sure it was great. The way I know Tim is through the many excellent researchers he has trained in physics education research and the really impactful work that I'm sure he's going to tell us about today. So let's welcome him.
All right. Fantastic. Thank you so much, and thanks for taking time out. It's like gorgeous outside, so I feel like the bar is pretty high for me to warrant an hour of your time here. Yeah, my name is Tim Stelzer, and I want to begin by saying, just interrupt me during the talk. I'll try to be looking. You can try raising your hand, but if I don't notice you, just shout out, because for sure what you have to say is more interesting than what I'm about to say. As was said in the introduction, I theoretical particle physics, that was my training. I did my graduate work in that, and I did a couple of postdocs in that area. And I will tell you that, I was always kind of had this hope, right, that I could be sort of like Richard Feynman, right, just have these deep thoughts and come up with these amazing insights. But I think if we ask Ulrich, I think I don't want to put words in your mouth, but I'm pretty sure that he would be willing to vouch that I'm no Richard Feynman, okay? But what I was able to do in high energy physics was take the genius ideas of somebody like Richard Feynman and Feynman diagrams and apply those and do something that I think was useful and did make some contributions. And that's also my approach when I do physics education research. So I don't have some, amazing insight into how people learn that's going to change all of education. Mostly what I'm doing is I take ideas from people that are much smarter than me and then, try to apply those and do useful things with it. And one of the things that lets me do this is I happen to be extremely fortunate because I work at the University of Illinois, which I like to think of as the Large Hadron Collider of physics education research, because we have almost 3,000 students taking our introductory physics courses every semester. We have 80 TAs helping teach those and 18 faculty. So we have what they call luminosity in high energy physics. But you need more than that to do good physics. You also need good experiments. And this is the part that I'm going to tell you about a bit, is that we have those. We are running high-quality experiments where we're trying things in lectures, which we think are the best things that we know how to do for lecturing. For our discussion, our recitation sections, we're trying, again, things that people have said are the best things to help students learn. Similarly, with homework, we actually have our own homework system, so we can program it to do anything we want it to do and see how that helps students. And our labs, in fact, we designed our own hardware for that, so we can do, again, innovative things in labs and just get lots and lots of data on it to see what works and what doesn't work. But it wasn't always like this at the University of Illinois. Well, it was always like this. We had a lot of students and a lot of faculty, but it wasn't really a good place for doing physics because really we just did a terrible job teaching our introductory physics courses. And so the story was, in fact, the only people that taught the introductory physics courses were associate professors, okay, because they're these large courses. If you gave an assistant professor the job, they would never get tenure, and full professors just said no. So the only one you could get to do it was an associate professor promising them they'd be full professor. So it was really bad, but it was so bad, in fact, that the College of Engineering said, this is so bad that we're no longer going to require our students to take your physics courses because they're not learning anything. And, okay, well, that's fine. That'll make it easier. And they said, well, that also means you're going to have to reduce your faculty by a third. Okay, now people are concerned, okay? This is a big deal. And so there was this crisis that was really happening. And, the whole faculty got behind this, like, okay, we're going to improve these courses. And it's not like all the faculty worked on improving the courses, but it was this nice thing, like, I think there was about 8 or 10 faculty that said, okay, we'll do some heavy lifting. They got some release time from teaching. But the other thing is, the other 40 faculty were all cheering them on. They were like, okay, this is good. We really want you to succeed, and we're going to support you. And so when we had to make this change, there's a couple ways you can do it. One way is say, well, let's just make it just good enough so that they don't threaten to take all the students away. Or you can say, well, let's just do the best thing we can do. And here, I think the department does deserve credit, not me, but the head of the department saying, let's just do this right and do the best thing we can do here. And so we kind of took the model that, well, we know how to research really well, and we should sort of apply these same skills to trying to improve our courses. And so the first thing to do, right, you do your background, you find out what are other people doing. No reason to reinvent the wheel, so we went around the country looking at that. Think about how you adapt it. Every environment is different, so we did that. And then a key thing is you're going to need to do some innovation, right? The stuff that's needed for your place is definitely, is probably not just out of the box, so you're going to need to put some energy into doing that. And probably the most important thing is measuring the impact, because basically I'm going to tell you several stories, and in each story it's going to get old. What happens is we have a great idea, we implement it, it fails, we figure out what we did wrong, and then we improve it so that it works. And so you need to measure what's happening with these. We did that. Lots of infrastructure to support the faculty in doing this. I just want to be super clear here. At the University of Illinois, like a lot of universities, your career depends 100% on your research, okay, full stop. And so you cannot participate in activities that negatively impact your research, no matter how much you care about them. And so you need infrastructure so that it's not negatively impacting your research when you're working on this teaching. And really adopting a team teaching, and this has a big impact. So, we have several people teaching one of these courses, and you really are entering a collaboration when you're doing this. Like for this semester, it's the 3 of us, trying to teach the best course we can, and that had a big, big positive impact. So that's the idea. Now I want to take you through a few of the things that we did along the way and show you how they worked or how they failed. And we'll do a few of those examples, and then I'll talk to you at the end a little bit about what we're looking at doing next. So the first thing that we thought, this will work for us, Eric Mazur from Harvard was going around the country talking about peer instruction. We thought, great, we can do that. And the idea is that the lecturer, instead of lecturing the whole time, will periodically stop, give a problem to the students to answer, and then they give you the answer, and then you go on. And so let's go. I think it's nice to have a concrete example because you're probably all thinking, like, what kind of question? So we're going to do a question here. This is right from one of my lectures, and it's when we're doing light. And so here's a person that, here's the physics. Remind you that when light bounces off a mirror, the angle of incidence is the angle of reflection. And so a person here is looking in the mirror. They see their knee at the bottom of the mirror, but they can't see their shoes because that light goes above their head. So they have this clever idea, I'm going to take a step closer to the mirror. When they take a step closer to the mirror, what happens? Does it make things worse? They just see above their knee? Does it not change things at all? Or does it make it better? Can they see a little bit lower? And so you can't put a physics problem up there and not give you guys a chance to do it. So I'm going to give you 1 minute. Talk to the person next to you. Tell them how smart you are about mirrors, and go ahead and do that. So go ahead, chat with the person next to you. You can say it as loud as you want. See if you can figure out what happens here. Oh, he's trying it with a camera? All right, what do you think? It's hard. Yeah, it is a good reason to think it's 8. What?
Unless it's some kind of trick question.
Yeah, exactly. All right, I'm going to ask you to stop, just like I would in class, and then we'll have you vote. That's the way the peer instruction works. And so the way we're going to vote, we don't have our phones out here. You're just going to do A is 1, B is 2, and C is 3. So just in front of your chest, say what you think the answer is, okay? Let's see, everybody. There we go, trying to get a sense. All right, very good. We get good representations from 1 and 2. I didn't see so many 3s, but maybe it's because my eyes aren't good. The correct answer is, I really did that in lecture. It doesn't change it at all, okay? And of course, in lecture, I have the demo set up, and somebody does this, and you can see what happens. You get closer. Of course, when you're closer, you can see at a steeper angle, but the light is also coming from a steeper angle, and they exactly cancel each other out. So this is an example of a peer instruction question, and there's lots of reasons to do this that we know about how people learn, and so I put them up here. There's this idea of resetting the student's clock. Assuming your students are human, they can pay attention for about 10 minutes, okay? And then you need a chance to reset. It promotes discussion, and discussion is important, right? A great way to learn things is by trying to teach them or speak them, and so you're doing that. We know that's good. Feedback to the students. Everybody heard the angle of incidence equals the angle of reflection. Oh, that's easy, I know it, I understand it. But when you ask a question like this, you say, well, no, I'm not going to say it comes in at 35 degrees, what does it go out at, right? I'm going to ask something like this. So feedback to them, and of course to the professor to see, like, what I said was brilliant and clear. Did the students get it or not? And so lots of great reasons. This is just a no-brainer. This is a win-win-win. So we implemented it, put it in our course, in our lectures, and it failed. Does anybody know why? We didn't know, but you're all smarter than me. I thought it would just work. Can anybody tell what the failure mode was, or can you guess? Do you have any idea why it would fail? Yeah, and I would say even stronger than that, most students just don't want to participate after a while. Like the first lecture, they'll all participate like you did. But remember, if I did 8 of these this lecture, well, most of you participated in the first one. I'd lose half on the next one. And pretty soon, so by the 3rd week, nobody's doing this because, well, Professor Stelzer is going to tell me the answer, and I don't want to feel stupid, and people can see, some people look around and they see, oh, he voted 3. He doesn't know what's going on. So it's a real problem. But it's so good for people. Yet there's this barrier to doing it. And so that is the reason that we developed the iclicker, because the students had no motivation to participate. I couldn't give people points for showing me fingers, I guess. And so, I was about to say the wrong thing with that. actually what we had was flashcards for them to show. And they could get embarrassed by their peers, not the person they're talking to next to, that's their friend, but it would be, somebody across the room, right? Just seeing, oh, they look stupid. And so this way, they're now anonymous to their peers, and I can give them credit for participating. And so now we could get the power of this happening, and it was really, really nice. You got students engaging, talking, and I said, sorry, I didn't say this. My class that I'm teaching this semester, I have 900 students, but don't worry, we don't teach 900 at once. We break them into small groups of 300, and so we can do this. But I think it's an auditorium with 300 students that are 19 or 20 years old, and they're talking to each other. There's so much energy, right? It's the professor, blah, 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 and then suddenly it's just loud like you're at a basketball game. Okay, reset, and then you go back. It really had a nice effect. So when you're, sorry. We have 300 in a room. That's our biggest auditorium, yeah. Yeah. You don't. Yeah, exactly. So this is working great. Now, of course, I showed you a question that was what I consider a good question because, in fact, when we do this to our students, it's usually like 30% choosing each one. And so you want a question at the right level so that they can think about it and talk intelligently, but it's not just a trivial answer that makes sense. So what we want to do is we want to come up with questions that are at the appropriate level for where the students are at. So how do we do that? Well, again, we looked around and we stole an idea from the Naval Academy, something called just-in-time teaching, where what we do is we ask the students, and by ask I mean we give them points if they do it, is to fill out a survey before each lecture, and it asks a few questions about the topic of the day that we're going to talk about. And then they get points not for getting it right or wrong, just for participating and doing it. And here is an example of one of those questions that we asked them. And this is, again, from the light topic. So I don't know if you ever noticed this, but if you look at an ambulance, they have it written backwards on the front of the ambulance. Does anybody know why they do that? I'm not going to do a thing. You know? Yeah, exactly. So in case you didn't hear the 120 decibel siren or see the flashing red lights, you'll read ambulance and pull over to the right-hand side. Okay, but they do. Okay, so that's fine. And, it's a nice left-right symmetry thing with mirrors. And so this is a response. So a student said, they can read it in your rearview mirror, just like you did. But there's something strange about this response. I don't know if anybody else sees it, but why did they put an exclamation point there? Why are they excited about it? Well, it turns out they are, and let me show you another response. Okay, there is no credit for getting this right. All they need to type in there is anything, because my mom loves me. And they get the points. They're talking about calling their friend who's an EMT to ask about this, right? And 3 exclamation points, right? They are really excited about telling me the answer to this. And so those other 2 are common. Here's my favorite, and I'll just let you read this one here. So I should tell you that in lecture, I do just what I did for that one. I include the response, a response or 2 from students and put it up there, but without their name on it. And so this person here was pretty industrious with a plan that they could use that to get to know the person next to them. And I can tell you, so I can see the names of the people that do this. So I knew the guy. I mean, I knew like the name, then I knew the person. There's somebody that actually came in early, so I knew who this person was. But I didn't know who sat next to him, and so not when I had this up there, but later in that lecture, at one point, I was kind of curious, like, who's the person that inspired this message? And so I did notice. And, okay, the guy that wrote this, I don't know, whatever. He's 19, 20 years old, athletic, I would say handsome, I don't really know. But the girl sitting next to him, he didn't have a prayer of ever going out with her. But he put it up there, and well, you can ask me if you want during question time. I can tell you how this story ends, because there's more to that story. Okay, so this is great. Now, the thing that I did this for was I wanted to know what the students knew and didn't know coming into lecture. But what I found out, there's a much bigger effect. Having them type responses to me and having their responses up on the board had a huge effect on the students feeling engaged in the class and part of the class, and really changed the climate of that lecture classroom when they were doing things. Of course, we also found out what the students were learning from reading the textbook so we could do the questions right. And this terrible thing was they were not understanding anything in the textbook. We would ask the most basic questions, like we kept doing easier and easier ones, like they were learning nothing from the textbook. And so we wanted to understand, why are they not learning from the textbook? And so we did a survey, and it turns out the reason they're not learning from it is you have to read the textbook to learn from it. It's a fundamental flaw in textbooks, I think. And so I had these students, right, that are writing essays to me, right, calling their friends, trying to answer these questions, but they're not reading the textbook. And of course, in lecture, I want to spend the time doing the hard stuff, not the easy stuff. I want them to read the textbook, and so we can really concentrate on the hard stuff. So, well, what can we do? Well, we think, well, the issue is I can't tell if they read the textbook or not, but I can tell if they did the checkpoint. I can tell if they click with the clicker. So we said, well, what if we put something online, like a pre-lecture that we asked them to do, because then we can tell if they did it, and we can give them credit for doing that. I'm like, okay, that seems like a reasonable thing to do. And I want you to know that these are not like recordings of me lecturing. These are really meant to, you can see there's no person there. It's really just displaying the physics. It's less than 15 minutes of narrated and animated things, and it's broken down into small bite-sized chunks, and it even includes embedded questions. So we thought, well, why don't we put those in? And it turns out that if you're going to do multimedia, there's some advantages you can take care of, because it seems that the way people work, I don't know, see, I don't actually know where everybody's from here, but have you heard of working memory? Is that something that people have heard? Or short-term memory? Is that something? Okay, so apparently for humans to understand something new, the concepts that you're putting together for the new idea, they all have to sit within your working memory. That's how you, quote, understand it and then can put it into long-term memory. So that's a bottleneck. That's a 7 plus or minus 2. So that can be a bottleneck for complex ideas, and physics is full of complex ideas. But here's the cool things about humans. Humans have 2 working memories. We have the visual and the auditory. And so the most powerful way to learn is to have 2 different representations, visual and audio, for the same idea. So you're basically just getting a lot more working memory processing this. So we're going to make these video animations, and so I can control what the student is hearing, right? Because I just pipe it through the speaker or through their earbuds. But what they're looking at is harder to control, because the way our eyes work, you have a huge range of vision, but what you're focusing on is very, very small. So if you look at the screen up here, you can't actually focus on that whole picture of the brain. You can only look at a very small part. And we need them to be looking at the part we're talking about. So we want to see, are the students doing that? Otherwise, we don't get this effect. So, and there's lots of research showing that, combining these 2 things is a very powerful way for humans to learn. These are actually books, not just journal articles, but they're books, so it's well established. So we can do that. They have these things called eye trackers, and it can tell what you're looking at on the screen. So these are used a lot for advertising and stuff to see what's going on. But you can also use them for education. And so I'm going to show you here. I have an example. So here's an early version of the slide. It's before we knew these worked. And so we're talking about superposition. And the way to read this is this dot is what the person is looking at. And this trail, like they were looking down here, and then their eye went up there. So you're going to watch this and listen to what's being said and see if the person is looking at the thing that we're talking about. So let's go ahead and do this.
Positive charge if there's a negative charge directly to the right and another negative charge directly below it. The answer is that the net force on the positive charge.
Okay, well, I don't know. I know it was very, very quiet, and you probably couldn't hear it too well. But basically, the person was looking at what we wanted them to look at the whole time. So it seems like it's working really well. But maybe this is just a smart student that understands, so they're following what they're supposed to follow. I want to control what the student's looking at. So even if they're totally lost, they are looking at the thing I'm talking about. So if I can do that, a way to demonstrate I can do that is I'm going to try to make the student look at something that I'm not talking about at all. Right? That means I'm overpowering their free will. Oh, it feels so good. So what I'm going to do is I'm going to try to get them to look at this, F31, right? Nobody looked at it before. We're not really talking about it. Let's just go ahead and look at it, see if I can force the student to look at it. Here we go. Second attempt.
Charge if there's a negative charge directly to the right and
got him.
Another negative charge directly below it. The
Got
answer
him.
is that the net force on the.
Oh, come on. It's too easy, right? So it turns out humans are designed, if something moves in your peripheral vision, you will look at it. You don't have a choice about it, right? Because if your great-great-great-great-great-grandparents didn't look at things moving in their peripheral vision, right, they were eaten and they didn't have kids. And so you have no control over this. And so it's fine. We know how to force what people are going to look at. And think about it. It's what we do when I'm speaking. I'm sitting here with this laser pointer. You think I'm being all friendly. No, I'm forcing you to look at something because it's moving. There are other implications for this. And this is a thing like when you have, laptops and stuff in a classroom and that when stuff is moving on the screen, people are forced to look at it. It's not a matter of having discipline or anything. It's just, you can't help it. So this is an important thing to understand. We applied this, and let's see if it works, okay? So let's see if some physicists can get this thing to work. So we did a study where we paid students that were taking the mechanics course to be in a study where we were going to teach them some E&M, just the beginning of E&M. And one group of students we had read out of a textbook, and the other group watched some pre-lectures that we had created on the same topic. And so what we had them come in the first day, they do a Coulomb's Law pre-lecture, or they read. And I will tell you, like, this is happening in a lab setting, so they actually read the book, like they were getting paid and they were being watched. So they read it. And then we gave them a test, and the test questions are something like this, comparing forces, not hard test questions, but did you get the idea? Then they did another unit, and then they took another test on that one. Then they went home. They got $20 or something and went home. They came back 2 days later, and we did 2 more. We did field lines and Gauss's law. And then they went home, and then there was Thanksgiving break, and then they came back, and we gave them a test on all 4. No new content, but on all 4. I wanted to see, how did they do? What did they learn? And the results were pretty encouraging. We saw that the students who watched the pre-lecture scored about 13% higher on the exam than the people who read from the textbook. And this was encouraging because they call it an effect size of 0.7, but it's basically exactly what the textbooks said you would see. It's what all their results had been. They weren't in physics, they were other things. But we see this huge gain. Okay? Now, anytime you see a histogram, you should be nervous because it means I'm hiding a bunch of data from you. And so let me spread that out a little bit and show you how each of the students did. So students that saw the pre-lecture, they're represented by a blue sphere here. And students who read from the textbook, they're a red pyramid. And I separated them out based on how they did in mechanics. So this is an E&M test, right? They're taking mechanics. It's E&M content, so they haven't seen it before. But basically, you know, the stronger students on the right, the weaker students on the left. So you see we have a bias here. We had the three strongest students all were on the pre-lecture side of things. But you see all the way throughout, the people with the pre-lectures are scoring higher than the people that read the textbook. That should happen. So it's pretty good, yeah? It was good enough for us. It convinced us to create a whole suite of these pre-lectures, which was a ton of work, and put them into our class. I put them into the class, and it was really fantastic. It was such a great semester doing this. And one of the things we looked at is how did they do on those checkpoint questions, those just-in-time teaching things, right? Because they weren't reading the textbook before. They weren't doing very well on them. Now they are. And so let's see how they did. Well, first, you always have some students that choose not to do it. Okay, so here, these axes here are the scores that students got before we had pre-lectures, and here's the scores they have afterwards, but these are just for students that chose not to do them, okay, because they can still choose to do that. And so you see things are basically right along the line here, meaning if students, just like the textbook, if they don't read the textbook, they don't learn. Turns out if they don't do the pre-lectures, they also don't learn. But this is a minority of the students now because we're giving points for this. The students that did watch the pre-lectures look very, very different. You see almost everything is above the line, right? So they are coming to lecture much better prepared. And you see there's one point that's distinctly below the line. There's an interesting story about that one. I'm happy to tell you if you want to hear about it. But huge success. Lecture was great. It was actually tough because University of Illinois, they're bright students, but if they haven't read the textbook, they're pretty much harmless. They're not going to ask you anything that you can't do. These students now were coming in, and they were asking embarrassing questions because basically all of introductory physics is ignoring things that make it complicated. And then these students now are asking things, and they're asking about ringing and circuits and stuff like that. Like, no, you're not supposed to think about that. It was absolutely fantastic. Now remember, in the clinical study, we saw a 13% improvement on the exam scores. And I'm thinking, hey, I'm getting paid for teaching. They have to determine what my raise is next year. So I talked to the department head, and I said, hey, I did a bunch of work on this. Let's make a deal. Let's say my raise is whatever the improvement is on the final exam, because we repeat final exams. This was Dale, yeah. And Dale says, yeah, that's fine. That seems reasonable. So I'm like, I don't know. Maybe at Brown you guys get big raises, but for us, like we get, actually we had several years with 0%, and then, 1 or 2% raises. So this is a much bigger raise than you get when you get promoted, 13%. So he says yes, and I'm all excited, and I'm like, sweet. Or like, guess who's going to Hawaii? And my family's happy, my wife's happy, and we go, and yeah, that was the deal. How could it go negative? Yeah, I'll take the risk. It's not going to go negative. The semester is going great. So I give the exam, the final exam, and these are the results. They score 1% higher than in the past. And to be fair to the department head, he was true to his word. I got a 1% raise. Like, what happened? So I talked to one of the students, right? And I was like, how was the semester? So that was great. I said, yeah, it seemed like the question was, great, yeah. And I said, well, why didn't you do better on the final exam? He's like, what do you mean? I got an 88%. I'm like, yeah, you were supposed to get 98. And then he looked at me, and he told me something that just shocked me. And I checked. It was true for him. I checked, and it was true for other students at the University of Illinois. And I don't know, it might be true at Brown. You should find out. But he told me that he was taking other classes. Yeah! No, physics wasn't his only class. And he knew what grade he needed in physics, and so then he started studying calculus and doing his other things. And yes, it's so obvious afterwards, but it was not obvious to me. But of course, they don't just say, oh, physics is a 4-credit course, so I'm going to spend 8 hours studying physics and learn as much as I can. No, they're always balancing. And so I did all this work so they could do better in calculus. That didn't feel very good. And so I wanted to somehow, I've done something great here. Somehow I want to be able to measure it. Fortunately, we survey our students to death, and we always have, fortunately and unfortunately. And so one of the things we've always found out about this course is 80% of the students say it's one of the hardest courses. Before we did pre-lectures, 80% of the students said it's one of the hardest courses they've ever taken. This is electricity and magnetism. And that's a lot. That's a lot of people having trouble. After we made this change, only 40% said that. So in fact, it was working just like in the clinical study. They just chose to spend time on other things. A couple other things that we asked in the same survey, and these are probably correlated, is what's your attitude towards physics? And when it was this hard, their attitude was not very good. And what was even worse is they said, I love the professor. We always tried to put, after this change, we always put good professors in there. Said, I love the professor, but physics just isn't my thing. I just don't like it. After we made this change, 80% said they like physics. Okay? And they like it in the right way. They said, look, I don't want to be a physics major because I want to make a lot of money, but I think physics is really, really interesting, and I like it. And then the last thing, which to me was one of the most important, is before we did this change, we asked them how important is the lecture for helping you learn. And only 40% said the lecture was helpful. Right? Just 40%. And so that's not good for me keeping my job. After we made this change, it was 80% were saying that the lecture was really important for them learning. So even though I didn't get to go to Hawaii or get the big raise, yeah.
How many people are coming to lecture?
Yeah, well, that was the thing, is they come because, we give them points. So I'm not sure, I'm pretty sure if we didn't, they wouldn't come. But yeah, and actually it even created a problem because we counted on people not coming, so we had more than 300 people in the thing, and we had people out in the hallways, and we got in trouble and stuff. So, but yeah, basically 80% of the people show up, and it's different people on different days. So yeah, but I attribute that to giving them points. But again, a lecture can't be valuable if you don't come. So there it is. That's one study. How am I doing on time? I'm going to run out soon. So we'll go kind of quick for the next one. Another thing that we look at is their online learning, right? We have a large course, so we definitely do online homework. And we do some of the worst kind of online homework, calculate the force, type in the number, you're wrong, you're wrong, you're wrong, you're wrong, you're wrong, you're right, okay, go on. That's how most of it is. But we wanted to try something better based on mastery learning. And again, this is a new idea from the 1960s, whereas the idea is that, everybody can learn the thing they need to learn, but people need different amounts of time and different amounts of practice to do that. And so that's the idea of mastery learning. And there was some real hope that it was really going to transform education, but it didn't, because implementing it was just not really feasible, having people going at these different paces and stuff. But we thought, well, maybe we can build on this. And so we made a homework system, or a homework problem type, where what happens is a student comes in, they try a set, in our case it was typically like 5 questions to do, and then we tell them which one of those questions did you get right, and which ones did you get wrong. If you got any of them wrong, then we we gave them solution videos that they could see for any of those questions, which they could study. And then we gave them another version, which they can do, and they can stay in this cycle getting as much practice and help as they need until they get 100% on it, they've mastered it. And then they go to the next level, and they repeat it, and you can try a more difficult thing. And then they go to the next level. And then if you have that good of a graphic, the NSF can't help but fund you. And so we built these. And again, I just want to show you what it looks like. So we'll talk about capacitors. And here we're trying to get them to learn to know if capacitors are in series or parallel or neither. And so we give them a circuit, and we ask them about different combinations. This one is C2 and C5. Are they in series, parallel, or neither? And the student answers them. And once they have all their answers entered, they click submit. And it tells them which ones did they get right or wrong. In this case, the student got 3 of them wrong, so they have partial credit. So then they can watch videos that explain how they were supposed to do it. And then when they feel like they've studied those enough, they can click, I want to try another one. And now they try it with blue capacitors instead of green capacitors. And this time, if they learned it, they get it all correct, and they get 100% and can go on. So that's the idea of what we're doing, and they can go through this cycle. And I should comment that we don't have an infinite number of these, so there's actually just 4 different attempts that they would have to get it all right. Okay, so again, we want to test. It seems like a good idea. Does it work? First thing we do is we pay students to do it. And when we pay them to do it, so I'm going to go fast here because this is just showing you there's a lot of graphics there, so it must have been a good study. And so we had some people do that, and other people basically do regular type homework, the same problems, but with immediate feedback and no mastery type thing. And then we looked at how they did, and we saw the mastery students did better than the regular homework. We also paid some students, and they had done the lectures and everything. This is happening during class, but we didn't have them do any of the homework, and we just had them take the test, and they got a 10% on it. So this was a really hard test. But you can see the mastery students did better, as expected. And again, we can show you pulling that out. Each one of these is not a student, but it's the different questions. And you see on every single question, the students that did mastery homework did better. So it seems to really, really work. We put it in our class, and it couldn't fail. Well, it did, okay? That's my MO. So I put it in the classroom, and it fails. And the reason this one failed was there were 2 things. One, a detail I didn't tell you about is the score you got for that mastery was always whatever the last score you did. So if you got an 80% on the first try and a 40% on the second try, your score was now 40%. And you only got 4 tries. So after that third try, if you got an 80%, you're like, should I gamble it? Could I get 100%? Or should I just take my 80% and go? Huge amounts of stress created. And so it really failed on that front. And then also, you need to make sure the different versions are similar enough that they can succeed as they go through. But, we learned and we made them better. And after doing that, we had a nice implementation here. And again, we see a huge difference. People that did mastery did much better than the people using the regular homework on a couple of different activities. So there you go. You get the idea. And so, so no, not my standard model of physics. This is my standard model for physics education research. It took me a long time to learn this, but I think it's true. And I just have a little nice video here to show you, how the right way to think about students and student learning. So here we see a robot that has done machine learning. Yeah, it's pretty impressive, right? It turns out that is not the right way to think about student learning. That's how I was thinking about it. This is a better way to think about it. All right. So you're saying, wait. What does that have to do with student learning? Well, what it has to do, so this I use this when I teach mechanics, at the very first day, I say, this is the amazing thing. This semester, F equals ma, it's going to explain everything that happens with that bottle, from the trajectory, the rotation, the rocket thing happening everywhere. It's going to explain everything about that bottle except why the person chose to do that. And the thing is, it sounds stupid, but students are a lot like people, and we really need to embrace that fact because students get frustrated. Machine learning does not. And this is a huge part, and so this is what we're really focusing on moving forward. Sorry, yes?
If I do this 100 times, I don't think I can get this once.
Yeah. It is very impressive, yeah. Humans are amazing.
So this would not be a dumb thing he was doing. Maybe he's trying to demonstrate it.
No. I mean, look, he's videoing it. He's doing this intentionally. This wasn't. This was a skill shot here. This was not like, oh, I'm so frustrated. I don't know if he wanted it to hit him, but I think he wanted all the rest of it to happen. So what's next? Well, I think the biggest challenge facing us now is diversity, equity, and inclusion. And you can see lots of plots that will show you. Here's the thing that you'll see showing like our Hispanic and African American enrollment in physics are getting degrees. And the thing that annoys me is they don't even include what the benchmark is. You just see these low numbers. I don't know, is that bad? But here, they're off by factors of 2 and 3 from where they should be. And similarly for female representation, we're just way, way off. And here's the thing, is that at Illinois, 10% of our students don't pass mechanics on their first try. Okay? And so this cliff here that people are climbing is actually introductory physics. They need it to go on to engineering, not just physics, but any engineering degree. And even worse, like as bad as 10% is, it's much worse for underrepresented groups. And so this is the thing that we want to try to address. And let's see. So I'll just kind of give you an overview of how we're thinking about doing this. And I kind of like the analogy. I think that's sort of an education thing. We like analogies. So I would say that things like the flipped, the peer instruction, the flipped interactive lectures, the mastery homework, those are kind of like footholds and handholds for people trying to climb this mountain of introductory physics. They're key. They can help you do better. And in fact, for a lot of students, that's all they need, right? 90% of our students are passing. But it's not enough for everybody. And the piece that seems to be really important, especially if you're on the borderline, is social connections. And I think that it's nice to think about that as like your safety rope. Okay, those social connections. Again, if you're super strong, it's not a big deal. You just climb up you just scale the cliff and you're fine. But if you're not, if you're shaky, this is really, really key. And it's key for 2 reasons. One, of course, if you slip, it means we don't just lose you. Okay, the damage done is less. Also, it gives you confidence to push yourself further than you might have otherwise because if you slip, it's not all over. So these are social connections. We try to do it now, but we're not doing it very well, and that's the area that we want to improve on. And now I'm going to give a phrase that I'm really surprised to see myself put on here, but it seems to be the key. This thing we're calling, it's socio-emotional risk. We're not calling it that. But really, this seems to be the right lens to try to understand these interactions for students. And it's the part that we think if we focus on this in the interactions that we're setting up, that we can really create this strong lifeline and really make a difference in terms of our pass rates for students that are at risk. I'm almost out of time, so I'll tell you that we're doing this in many fronts. We're also trying to work on our teaching. Again, we have 18 faculty, 80 graduate students, and these 60 learning assistants, which are undergraduate students. Happy to talk more about that. They have a big impact. But again, the big idea, the teacher can't carry the student up the cliff. You can't just carry them up. They need to climb, but the idea is they can point the route and show them a safe way to get to the top. And a new thing that we're doing that has been incredibly time-consuming and very satisfying is we created a partnership program with high school, in-service high school teachers. Right now we have 40 teachers in the program where we're working with them to create a community so that they can strengthen their skills, because we know for the pipeline that high school teachers have a huge impact on students deciding if they want to go on science or not, and so we're working to support them. And I think now I'm right at my 50 minutes, and so let me stop right there, and thanks for your time, and asking the questions.
Plenty of time for questions.
Or I have more slides, so questions would be better. In the back. Oh, yeah, so that's a great question. The question is, are we going to be able to use artificial intelligence to help tailor? And I had a slide up there. Actually, I have a slide coming up. And I would say that, that for me, the place that I think we can get the biggest help for artificial intelligence, or for machine learning, I should say, really, is in helping us with grading. So we do not grade handwritten homework, and one thing that it can do is categorization. And so it turns out if you're grading papers or written work, and you have a bunch that are very similar grouped together, you can grade them much faster. So we have an issue of grading at scale, right, with 900 students and grading fairly. And so AI can potentially group them together, making that more efficient. As far as generative AI, I am so concerned because I think the right way to think about generative AI is it is designed not to have the right answer, but to convince you it has the right answer. So imagine that you were training TAs and you said, yeah, if you know the right answer, go ahead and tell them. But if you don't, just make something up and make it convincing. And that's what it does. And that seems like an incredibly dangerous thing to put, for training our students. And I know you're thinking about something different, and I think there probably are some opportunities there. But looking at the time scale, I see this one as an immediate problem. And to address it, we're going to put it into our class where we can monitor what the responses are and try to look at it. Thank you. Sorry.
Yeah, I was wondering what you do about assessment. I kind of remember some time ago there was a forced concept inventory, some standard tests that you had them take before and after.
Yeah.
You mentioned that you have control groups and compare on the same questions. So I was just wondering whether you could elaborate a little bit.
What we do for control, and that it varies from experiment to experiment. One thing that we do use is the final exams, because those are kept private, and although they change slowly over time, we can match questions and do that. We don't do the forced concept inventory, mainly because it's mechanics, and I mean, you'll be surprised to hear this, but at the University of Illinois, they just peg it. Like, we have a ceiling effect where most of the students just know their mechanics coming in, which is why most of the studies you'll see we were doing on E&M, because they already know their mechanics. And yeah, I guess that's.
Thanks.
Right, thank you. Oh, wow, you noticed that. Good eyes. So there was one question we said we did the pre-lectures. They did better on almost every question, or at least the same. Some it didn't address. But there was one that was like clearly below it. And that question was about total internal reflection and whether you could basically hide something in the pool because of total internal reflection would prevent the light from going out. And it was true or false. It was a 50-50 thing. And basically what happened is, when they didn't read the book, they didn't know anything about total internal reflection. They're just like, well, yeah, you can't hide anything in the pool. So they got it right at about the 50% level. After watching the pre-lecture, they knew about total internal reflection. They thought, oh, cool, we can probably hide something in the pool. And so only 30% got it right. So they were actually learning something, just that little bit of knowledge made them do worse.
That's really interesting. My other question was about that introductory course. I think you said 10% usually fail. How much of that do you think is a problem with the grading scheme, or like requiring instructors to have a specific grading scheme versus the students not actually learning?
Yeah, that's a really good question. And unfortunately, the way our grading is set up, so the people that fail really do not know mechanics at all. And so in order to do that, yeah, it's a concern. So it's not that we think the cutoff is too high, but I mean, it's our fault. It's not the students' faults. They're all smart and they're all motivated. We're just not giving them the resources they need to do well. So that's what I'm hoping. I'm hoping we can change. By the way, failing, I mean, if you get below a C, you have to take it over again. So people can, in fact, take it over. But what we find out is that 2/3 of the students that don't, that need to take it over, they don't end up getting an engineering degree. And one of the studies we did is we tracked down the students that did complete it, right? Because they're very special, and we wanted to find out, how did you survive, right? You should have failed. And they're fantastic stories. I mean, these people are amazing, and always the thing that saved them was social connections, right? It was a mentor, it was a group of students, it was something. It was always people. It was never, oh, I saw this YouTube video, and suddenly physics makes sense. And so that's why we're going in that direction. Thank you. There's a mic.
Thanks. So to what extent does these kinds of approaches end up modifying the actual choice of material that you teach? I mean, it's only human if some of these things are easier to handle with with certain kinds of assessment methods and certain kinds of videos and so forth, to concentrate on those. I mean, the example that comes to mind, if you teach a discovery kind of course, you may end up teaching a lot more about the conservation of energy of a pendulum than you are going to teach general relativity, because it's not so easy to discover that.
Yeah, so there's a good question is, did we modify our content with these courses? And I would say the answer is basically no, that there was no modification to the course in terms of the learning objectives. I would say we did, as many places did, more explicitly test on conceptual questions. I mean, that basically happened at the original thing. Missouri was going around the FCI, and so there was this understanding that people could do hard calculations and not understand concepts. So we did make that switch, but it wasn't because of our format. Yeah, it stayed the same.
So if I'm sold, and I'm thinking in particular, mastery homework sounds great. I'd really like to do something like that when I teach.
Yeah.
How do I get it without reinventing the wheel and getting teaching relief and building an entire online system myself?
Yeah, that's a good question. So, I mean, well, the nice thing is commercial systems are starting to put things like this in there. I mean, this is licensed to one commercial system, all these stuff that we did that, so people could just do that. But most of them are adopting it. So I think it will be an option when you choose what book you use or what book your students use. Or maybe, it will be like one of the choices, so maybe you choose the one that offers that. It's still an active area of research. They don't always call it mastery. What does Andrew call his? Andrew Heckler?
Essential skills.
Essential skills, but it's the same type of idea, and so I think it is catching on.
Hi. So I have a question about, I went to Penn State and I did an LA program, amazing. Did mastery physics too. Penn State also bought it off from the textbook. I have a question about the team teaching, because when I did the LA program, I know like we had to take a class before becoming an LA learning assistant. My question is how, when you started the whole 18 faculty, how easy is it to talk to faculty members to adopt this, and also because I'm sure everyone have like different teaching style, and how did that like affect the result of the final exam and everything?
Yeah, so that's a great question, and I should. One thing that I didn't make clear is that so the switching to team teaching and peer instruction, the team teaching happened right away. The peer instruction happened but failed, and so there's many years. This is not like 1 year thing that happened, and so I would say our experience is that switching to the team teaching is nearly impossible at university physics departments. I think we just got lucky because the crisis was so bad, right? I mean, this is like, faculty may complain about funding or salaries or office space or labs, but what they really care about is the tenure track lines. And so they were really focused on having this change. And anybody that said, oh no, I want my autonomy, no, we need these faculty lines. So I think it's a really huge challenge to make that happen. And we just got lucky because we had the crisis. But once we did it, it's been able to stay. Like, people realized, hey, this is great. And actually teaching and the team teaching thing is a better load. And in fact, that's an important part. Now when you're assistant professor, your first assignment is team teaching, so that you get a chance, to be part of a team where you have experienced people and you can pick up all these things like an apprenticeship model. So, if you have a benevolent dictatorship or something that can enforce it, make it happen, people will like it. But that transition, you're very astute, noticing that's hard to do.
All right, we're about out of time, so let's thank Tim again.
Great, thanks for your time.